So now this electron has to release that energy in the form of excitation. Okay? So it has to continue to radiate that excitation in the form of heat. So that vibration of that electron is given off in thermal energy. So kinetic energy was transferred into thermal energy by way of excitation.
Okay, thank you.
Make sense?
Yes.
Good. Come on, keep those questions coming. Those are good questions. That makes me think you're thinking. That boosts my confidence. Does she do that all day, Jaleisha, or just during PRE?
Just during class. Anytime I'm in class.
Maybe she likes my voice.
Anytime I'm in any class, she likes to come in. At least it's not my textbook.
I can't hear you, Jaleisha.
It's only ever during class that she'll come in here. She likes to lay across the keyboards and just lay there. Only when I'm studying or class.
Actually, I didn't know if it was my voice that was drawing her out. I actually have a senior. Her cat does the same thing. Like, she'll just come in and it's a wrap after that. Okay. Any other questions? Thank you, Jaleisha. Any other questions about PRE?
No. No.
Okay.
Stop it.
Okay, so let me ask you a question. I'm going to go with voluntold, and no, you know what? I'm going to volunteer on this first one. Volunteer. When I think about potential difference, who can explain to me what potential difference means in a nutshell? Maybe better than I can to explain without using all the physics terms to it. Who can explain potential difference? And why that is so important.
Come here. Here we go. Okay.
Ooh, I asked a great question. Woohoo! Love it. No one?
Potential difference.
Not yet?
Yeah, not yet.
Okay, so let me explain it a little bit. Let me explain. Let me see what I don't see, everybody. Okay, so let me explain. So tell me, so I'm going to start with this question. What is the diode that we have been studying for the last, 3-4 weeks? What is the diode that we have been studying in the last 4 weeks?
Diode?
When I say the word diode,
the vacuum.
Go ahead, Amy.
The vacuum.
The vacuum. When I say vacuum means empty space that lies inside the diode. But what does diode mean?
Is it the anode and the cathode?
It is the anode and the cathode. When you're talking about a diode, it has a connection for one part of electricity and a connection for another part of electricity. We know that one side of that die meaning two, conducting electricity. We know that one side is negative, right? And we have one side that is positive. Yes? Who can remember? Tell me, what is electricity? What is electricity?
Current.
I've said it, not 1,000, maybe 100 times. What is electricity?
Electricity is...
Yes, Shibu?
Current.
What you got?
Flow of electron.
Flow of electrons. And what kind of charge does electrons have?
Negative.
Negative.
Negative. A negative electron, or an electron, period. I don't have to say a negative electrons, because electrons are always negatively charged. Electrons are always negatively charged. Got it? So we have this diode, and we know that we have a negative side, right? Yes? Our electrons that are liberated, where are they liberated from, Ruth? Where are our electrons that are liberated? We have electricity coming in, which is a flow of electrons.
From the
Heating up. Okay, but where is specifically our electrons liberated from?
The filament that's being burnt off?
From the filament.
From the filament. So the filament has boiled off these electrons. These electrons are still negative, aren't they? They're still negative, aren't they? So when we say, so where are these electrons going to be attracted to? Where are these electrons going to flow towards?
To the positive side of the anode?
What is ever positive? Absolutely. It could be the anode. It could be something else. Electrons have to flow to the positive. Why? That is the law of electrostatics. I don't need you to know that now, but it is the physics phenomenon. The electrons will flow towards positive. Because there is the attraction of negative to positive, that is called potential difference. The attraction, the attraction starts the flow of electrons. The attraction, because the electrons are going to flow wherever the attraction is. If I move over here, it's going to flow this way. If I move over here, it's going to flow this way. It is going to seek to be a part of the attractive or positive side. Make sense? So electrons will always flow to the positive, no matter what. So the potential difference comes in is we know that the electrons are going to flow, and we know that the anode is positive, so we know that the electrons are going to flow towards the anode. Perfect. Potential difference increases and decreases in its attractive state, and it is measured in volts. Volts. V-O-L-T-S. Volts is our unit of measure to determine how attractive the positive is, or is drawing in the electrons. And this is going to make a difference. We're going to jump back into binding energy, but if we really think about it, how do we get the electrons to flow? We have to put them in front of a positive something, right? Something that has a positive charge. That's how we get electrons to flow. If I can create a bigger difference of attraction, meaning I go high in my attraction, my electrons will flow faster or slower?
Faster.
Faster. Perfect. If I lower the attraction, then my electrons will flow slower. They will still flow because there is a positive attraction. Okay? This increase and decrease in attraction is potential difference. I'll say that again. The increase or decrease of that positive attraction is called potential difference. And it is measured in electron volts. Volts is the unit of measure for potential difference, but as we start to incorporate how it affects these filament electrons, we're talking about electron volts.
I'm sorry, Ms. Locke. Can you repeat that one more time?
The electron volt. So what we're saying is, how do we get those electrons to flow over? We have to have a positive, attractive site for them to flow, right? How do we measure the potential difference? How do we know that we are increasing the reaction or the flow of the electron? We're regulating that flow. Does that make sense? The higher the unit of measure of volts, but what are we measuring specifically? The energy of the electron, the flow, and it's going to be an electron volts. Okay? And what we're going to learn, and you should have already read, because you're reading ahead from me, we're talking about the thousands and hundred thousands of electron volts. We will regulate the potential difference on how fast we want our electrons to flow. Okay? So I know it takes a minute, but we're thinking about the X-ray tube has been designed as a diode. It has been designed purposely to have electrons flow from the negative over to the positive. Why do you think that design exists? Why do you think that design exists?
To help create X-rays.
Anyone?
Design from negative to a positive.
Why do you think that design exists? Why do we have a negative side and a positive side on the X-ray tube?
So that you can easier correct the X-rays? Because X-rays...
So you can create the X-rays. Beautiful. You need a source of electrons. You need the electrons to flow. And you need to collide those electrons, don't we? That is why the X-ray tube is designed the way that it is. We want one flow. We want cathode to anode flow. We're never going to have it the opposite way. Make sense? Questions before we finish up characteristic and get into bremsstrahlung?
Ms. Laura, can you repeat the potential difference again? It's just the increase and decrease of what? I didn't quite catch that.
The positive attraction.
Okay, thank you.
Mm-hmm. So it's basically saying, Amy, that's not the definition of it, but it's basically saying, in a nutshell, if I increase the positivity of my anode, what effect will that have on my electrons? Go ahead, I can't hear you.
Oh, it's going to be faster.
Why? Exactly, because they're more attracted. They're more drawn to it, and they're drawn to it faster. Mm-hmm. So what happens if I lower that attraction?
It's going to be lower because the attraction is not as high.
That is the potential difference. The higher the difference between them, they're still negative. The higher the positive, they flow towards faster. If you bring down the attraction, they don't flow that. They're still going to flow, but they're not going to flow that fast. Make sense?
Miss Laura, we can't hear you.
Or see you.
Miss Laura, we can't hear you.
We also can't see you anymore.
We can only see her at the bottoms.
Can you guys hear me? Can you hear me now?
Yes, we can hear you.
I'm not sure why my video stopped. It says my video is disabled. Well, let me see if I can't share still. So let's see. But y'all can hear me okay. Can y'all see me on this other screen here?
Yes, we can hear you. And see you.
So let's see. Can you see my slides? I'm not seeing anything come up. Hold on. Well, that's no bueno. I didn't want to, I came home because I couldn't find an office, and I was at LBJ and I couldn't get an office. It was all occupied. So please forgive me. And let's see, are you able to see my screen now? Nope, you're not. Okay, well, I guess this is going to be a Q&A. I don't know. I guess I can't talk about the slides right now. So with that being, this is a left of me.
I have a quick question, Miss Laura. I know you said that.
Okay, I'm trying to reconnect me. Let's see.
Oh, can you hear me? No. Can you hear me? Oh my gosh, this thing is.
Well, keep the questions coming. If you have questions, keep them coming.
Someone's trying to ask a question right now, Miss Laura, but I don't think you can hear her. Can she not hear us? Miss Laura?
Can you hear me?
I don't think she can.
I don't think she can hear us, but we can hear each other.
Yep. Oh my gosh, this is driving me insane.
Oh, I hate WebEx.
Okay, but I can't hear you guys. So try unmuting and seeing if you can.
We can hear you now, I think. But can you hear us?
Miss Laura?
It's very dim. Hold up the volume. It's trying to reconnect me now. Yeah, it's unsuccessful. So I'm going to bring you out closer so I can hear you. Okay. So what questions do you have? I guess at this point, I don't know. I'm sorry, guys.
My question was, you said that to measure the energy of electrons, it's measured in volts. Is that correct? Can you hear me?
Yeah. Okay. So to measure, so what we're eventually going to get into, we talked about binding energy. Binding energy is measured in electron volts. Binding energy is measured in electron volts. The binding energy is measured in electron volts. So remember, if we increase the potential difference, and let's talk about characteristic. If I increase the potential difference and then my filament electron comes in and it's coming in faster, does it have the ability to ionize? If my filament electron is coming in faster, does it have the ability to ionize?
Yes.
The answer is
Yes. Yes.
If it's coming in faster, it has the ability to ionize. What does ionize mean again?
The release of an electron?
You broke it, right? You ripped it off of its binding energy. So that is going to be that. What is binding energy measured in is going to be an electron volt. That is the unit of measure. So when you go back to the slide where it talks about, and then also in your book, it'll tell you what is the binding energy of the electron sitting in the K shell.
It's electron volts and volts the same?
Volts is the level of potential difference. Electron volt is basically saying you're talking specifically about the electron. So the electron in binding energy. Now I can go back and say, okay, if I have electricity and I want electricity to run from one side of my cord over to the other, I'm going to have to put a positive in order to get my electrons to move, right? But those electrons don't have the binding energy because they're no longer in the shell of the atoms. These are liberated electrons. We're talking specifically about the binding energy of the electrons that are bound inside of the KLMNOP shells of tungsten atoms. So this is where we're talking about binding energy is an electron volts. So we'll go back to your slide where what is the K shell binding energy, and look at the unit of measure. What, Jesslyn? 69 what? There is letters behind 69. Or it'll tell you at the top. 69 what? KeV. The E stands for electron. The volts is the unit of measure, where we're talking specifically about the binding energy. And the K stands for what? 1,000 kilo, right? 1,000. So in essence, we're talking about thousands of electron volts of binding energy for that K shell electron. If you go back and you look and compare K to M, does it increase or does it decrease? It decreases.
It decreases.
So the further the electron is away from the nucleus, the binding energy becomes less. So let me ask this question. What is the ionization potential? Is it greater on an inner shell electron or an outer shell electron? If I were to ionize, remove, would it be easier to remove an outer shell electron or an inner shell electron?
Outer.
Outer shell.
But when you start to look at that, you start to say, okay, well, there is a higher KeV binding energy in inner shell than there is a binding energy in the outer shell, right? Yes? So when we learned about characteristic interactions, run that through me one more time. Who wants to tell me what is happening with the filament electron and the electrons that are orbiting the tungsten atom? Can anybody refresh my memory?
I'm gonna try.
Mm-hmm.
Okay, when the filament electron comes from is liberated from the thermionic emission,
Yeah.
it possesses kinetic energy, and it will interact with the electron from the orbit.
Yeah, of the tungsten over on the anode, on the focal track, right? Or the focal spot, yes.
Yes, ma'am. And then the interaction, if the energy is not very strong, we just get together and create an excitation.
So that the filament electron that was moving collided with an electron, but it probably did not possess enough kinetic energy to remove it. Maybe the binding energy was too high. So all of that movement got transferred into that electron, and that's excitation. But what happens when the filament electron does remove an inner shell electron from the tungsten atom?
X-ray is produced.
So a photon emerges, the binding energy photon, the binding energy that took that K shell electron and ripped it out of its orbit. That binding energy, which we know is how much?
69 point.
We know that it is high as 69.
Yes.
So the filament electron must have had equal amount of kinetic energy to, I'm sorry guys, to remove that inner shell electron. But there isn't, you know what, let me get off of it and try it again. Let me go ahead and just cancel and see if I can't get off and retry. So let me just exit it. Let me try that. I'm gonna open it back up. So let's see if we can't try to get back on.